Three of you. Okay. Anyways, good evening, guys. I'll just wait for one more minute. Let it become 5:05. We'll start. Yesterday, I think yesterday morning when you saw me, this beard was there, isn't it? Every time I take my beard, I feel so bad. But, yeah. Okay, fine. So we'll continue. We were saying the remaining reactions, right, in organic. So we have completed almost so many important reactions. Like last thing we saw was pinacol, pinacolone rearrangement. Hope you remember what was that. I need to have a vicinal diol, right? And actually, the last one was oxidative cleavage with HiO4, periodic acid, right? Okay, so we'll continue, right? So we'll continue to phenols, right? So generally, if I take phenols, right? So when I compare the acidic strength, right? If I compare the acidic strength of phenols with a normal alcohol, right? So I think you already know about this, right? So I hope you remember when we studied GOC, General Organic Chemistry, I told you that the acidic strength is decided with the help of stability of the conjugate base, right? And we know what is a conjugate base. After removing H plus, whatever is remaining is what is called as a conjugate base, right? So going by that trick, right? So if I check what are the conjugate bases here, so here you will get alkoxide ion, here you will get phenoxide ion, right? And obviously we know phenoxide ion is going to be more stable because of resonance, right? And here actually I'm going to have an R group. It's actually going to be an electron donating group, right? Which is actually going to increase the negative charge on oxygen, thereby destabilizing the alkoxide ion, right? But here, right, I'm going to have more stability because that negative charge is not going to be there on oxygen. It is actually involving in resonance, right? Okay, so that is one thing I want to make. So there will be a difference, right? For example, if I have ROH reacting with any metal, for example, sodium, right, it will react. Say it is going to form RONA, actually RO minus, Na plus. This is the salt which is getting formed, right? So acid, like acid with metal will generally give me salt plus hydrogen, right? Okay. Now, for the same thing, if I put NaOH, now it is a strong base, right? Now you will see there is no reaction which is going to happen, right? Now why? Because my normal aliphatic alcohols are not acidic enough to react with a strong base such as NaOH, right? But if I have phenol, right, and if I make it react with the NaOH, yes, now in this case, it will form a salt, O minus Na plus. This will form a salt. Obviously, with Na also, it will form the salt, right? So if at all you want to differentiate between your normal aliphatic alcohols, you don't know what is there, right? So if you make it react with sodium, both of them will react. But if you make it react with NaOH, only phenol will react. The aliphatic alcohol will not react, right? Okay, fine. So that is about the acidic nature of phenols, right? Now, obviously, you understand that my phenol OH group on the benzene ring is going to be an electron donating group, right? Electron donating in the sense it is going to give me plus R effect. Hope you understand how it happens. Right? Say, so if I have OH, right? Now what will you see is that there is a negative charge which will come here, and this bond I can make here, right? Say I'll have double bond OH plus. Now the bond is here. Now this bond would have broken, a negative charge which will come here, right? Now what will be the next step? This will go here, this will go here, and this will go here. So what you can understand is there'll be a negative charge formed here first in the first step, and then the bond will be formed. So what you understand is any electron donating group, right? Any electron donating group with respect to resonance in benzene ring will always be ortho-para directing. We already know this, right? Will always be ortho-para directing, right? Okay. What do you mean by ortho-para directing? If at all you're going to do any electrophilic substitution, say for example, you go for Friedel-Crafts reaction, right? Or you go for any other reaction, methylation, acylation, chlorination, bromination, whatever you do, right? The substitution will either happen at the ortho position or it will happen at the para position. Okay, right? Say if I have to give you one example, right? OH, say for example, if I just put HNO3 in the presence of H2SO4, right? This is my nitrating mixture, right? So now you'll end up with OH with NO2 here, or with NO2 here, either ortho substituted or para substituted. Okay, and you will have to understand that one of them is actually going to be a major product. Okay, one of them is actually going to be a major product, right? So let me tell you what will be the major product, right? Now, we cannot directly tell it, right? So what you have to understand is, people, if I have low temperature, right? If I have low temperature, then ortho will be the major product. Okay, and when I have high temperature, in that case, para will be the major product. This holds good for actually anything, like all the functional groups. This holds good again, given that it is going to be ortho-para directing, right? So lower temperature, ortho position, higher temperature, para position. So depending on the temperature, I'll be able to say which will be the major product, right? So generally, what do you mean by higher temperature? Anything greater than 100 degrees Celsius, right, will be higher temperature. Anything lesser than that will be low temperature, right? Okay, so that we know about phenols, right? Okay, next is, I have one reaction called Kolb's reaction. I think this reaction there in an NCRT, I'm not sure, right? So if you have phenol and if you just react it with CO2, right? So what will happen is at the para position, at the ortho position, you'll get COOH. See, I understand like this is H is already there. Now CO2 just get in between these carbon and hydrogen, so you'll form COOH. Mechanism not important. Don't worry about it. Okay, so Kolb's reaction is where I have phenol with reacting with carbon dioxide, right? You will end up with COOH. Okay, right? Fine. So that is Kolb's reaction. And next one is the famous Reimer-Tiemann reaction. Okay, so here what will happen is you have phenol, right? Now if you put CHCl3 in the presence of KOH, right, chloroform in the presence of KOH, right, you will form OH with CHO, right? This is what is called as your salicyl aldehyde. We already know this, right? Now, you might not know this. Instead of CHCl3, if I put CCl4 in the presence of KOH, right? Now, instead of this CHO, I'll be getting COOH. This is salicylic acid. Okay, salicylaldehyde and salicylic acid. Depending on whether you use chloroform, chloroform will give me CHO and CCl4 will give me COOH. Okay, now the mechanism for this is a little important. Okay, so we'll look at the mechanism. Right, okay. So people, what is going to happen here is, first I'll take this, right? So when I have CHCl3 in the presence of KOH, right? Now what is going to happen? Or say if I put OH minus, right? Now this OH minus, what is it going to do is that it is going to abstract a H plus from this. It is going to abstract a H plus from this. So you will form CCl3 minus plus H2O. Okay, CCl3 minus plus H2O. Okay, now obviously this table is little unstable. So from this, I'll remove the Cl minus. And if I remove the Cl minus, tell me what I'm going to form. What am I going to form? From CCl3 minus, if I remove Cl minus, what will I form?
Dichlorocarbon.
Absolutely true. Right? So you will be forming CCl2 double dot. This is the intermediate here. So this is one of the very few reactions, right? You will see carbenes as the intermediate. Okay, Riemann-Tiemann reaction, that's why it's little important. One of the very few reactions, right, where you will see carbene, dichlorocarbene as an intermediate. Okay, now if you understand that, then the next step is going to be easy. Okay, so now what? Okay, double dot. Now I'll have my phenol. Right, now this dichlorocarbene comes. Okay, right. Now what is going to happen is this double bond attacks here. Okay, now you will see OH, H, CCl2 minus. Okay, CCl2 minus, and the other thing stays. Okay, or if at all you don't want to confuse yourself, right? If you don't want to confuse yourself, you can look at it like this. Right, say I have my OH and H. Now if I put CCl2, this CCl2 is going to replace this H. Assume it like that. Okay, so I have CCl2. Okay, right. Now what is going to happen? Now you have the hydrolysis. Say you still have the OH minus present, right? You still have the OH minus present. So what is going to happen is this OH minus is going to replace both these chlorine atoms. Okay, it is going to replace the chlorine from the carbon, right? So next what will happen? You'll see that OH will be formed, COH, OH will be there, right? Then what is going to happen? Actually, there is a hydrogen missing. So it's not like it is going to replace this. You can just put a hydrogen here. This is going to get abstracted, okay, from this and to this, and then that adds together. Okay, so here there is a hydrogen also. Right. Okay, next what is going to happen? Obviously, two OH to the same carbon atom is unstable. So now you'll remove a water molecule. So the final product is OH with the CH. Okay, so the most important point here is that you are going to form a dichlorocarbene, okay, and the dichlorocarbene attacks and the OH minus replaces the chlorine atom with OH, and you'll form two OH to the same carbon atom, remove the water molecule, go for aldehyde formation. Right. Now, what is the difference if I use your CCl4 is that you instead of this, you will find CCl3 present. Right. Now CCl3 with 3 OH minus will form C, OH, OH, and OH. Now you'll remove water molecule and end up with COOH. Okay, that is the only difference if I use CCl4. Okay, pretty easy, right? The reaction wise, the mechanism wise, important reaction, right? Multi-man reaction. Okay, right? Did I miss anything else? No, right? Okay, fine. So that's about phenols. There is just one more reaction when I have ethers. I'll just talk about it, right? Hope there, oh, is there any question? If not, we'll move on. Okay. Right. So again, another name reaction. The name reaction is Fry's rearrangement.
Sir?
Correct. Yeah.
Sir, in case of the formation of salicylic acid, we'll get a trichlorocarbene.
So in that case, it will not be called as. So what will happen is that, yeah, actually in that case I cannot consider it as a carbene, right? So if I have CCl3, maybe I'll call it as CCl3 minus. But at that time, again, we don't have enough evidence to prove that in that case it is going to be a carbene. But yeah, we have sure evidence that in case of CHCl3, definitely it is going to be a dichlorocarbene. Okay, so you can assume it like CCl3 is going to come, CCl3 minus is going to come at that time. In that case, it is going to be a carbanion. Okay, but they will not ask you such questions because they're finding it out. Like these kind of reactions are still under investigation. You don't have to worry about it. Okay, right? Fine. So Fry's rearrangement, right? So this is given by aryl allyl ethers. Okay, aryl allyl ethers. Okay, I think from the name itself you'll be able to understand what exactly is happening, right? So I am going to have an oxygen attached to the benzene ring, right? Now obviously it's an ether. You see one of them is a aryl group, the other one should be an allyl group, right? Something like this. Yes, this is allyl group. Yeah, this is allyl group, right? Or if I have to write it properly, okay, that is better. Okay, this is my aryl allyl ether, right? Now it is going to undergo a rearrangement. Okay, so if I directly give you the product, maybe you'll just leave the class because so these kind of reactions are what are called as concerted reactions. Okay, these are what are called as, it is, or I would say it is going to follow concerted mechanism. Okay, concerted mechanism. Right. Okay, so what is going to happen is, right, is this allyl group, this is CH double bond CH, CH2. Okay, this is allyl only, no issues. Okay, so what is going to happen is this bond, right, this bond which I have here is going to attack this carbon and this is gonna go here. Am I right? Yeah, if I do that, okay, please understand it's like concerted. So this double bond attaches this carbon and this double bond goes and makes a bond here. No issues. Okay, but there is something wrong. I cannot just do it like that. Okay, guys, I forgot something. Wait. Okay, and now I got it. Oxygen. Okay, now what is going to happen is this bond is going to break and come here, and this bond will come here, and this bond will come here, and this bond will come here. You see the rotation. Again, I repeat. First step is this bond will break, make a double bond here. And obviously this carbon cannot have more than 4 bonds. So this bond will come here, this one, right? And obviously this carbon cannot have 5 bonds. So this bond will go here. Again, this carbon cannot have 5 bonds. So this will go there. That's it. This is the end of the cycle, right? So now what will you see? Okay, there is a bond here. Now you'll see that there is a double bond O, correct? And you see there is a bond here. right? And this carbon atom is attached to this. So say 1, 2, 3. So this is going to be 1, 2, 3. Okay. Now where is the double bond? Double bond, can I say it is here? The last two carbon atoms, there's a double bond, right? Anything else? Yeah, this one. Okay, right. Now what you see is this is the keto form. Am I doing correctly? Oops. Ooh, wait. This will come. Or if I directly attack it. Something I'm doing wrong. Just a moment, people. Where is it? Oh God, I'm not able to find. Okay, I have to check here. 1 second. There is some problem. What is the problem? This double bond comes here, or if I directly do it, this attacks. Okay, let me try that. Just give me a moment. I'll just try something. Okay, if I do this, a double bond O, and this carbon is attached to this. So 1, 2, 3. This one. and there is a bond here. Oh yeah, got it. Yes, fine. Right. So this is what happens. So I told you that there is one more step which I missed. Right. So this, I said this will come here, this will come here, and this attacks. No, but what happens is you see that this directly goes and attacks this, and this goes here, and this comes here. Right. Okay. Now what you see, this is the keto form. Right. Now if I undergo if this undergoes tautomerization, tautomerism, right, what will happen? You have an alpha hydrogen here that will be removed. So then it will go, you will form OH. So you will see that I'll form OH and this will be the product. Okay. Now look at where we started and look at where we ended here. Okay. So this is what is called as your Fry's rearrangement. Okay. Right. Okay. If you ask me what I have to do, you just have to heat it. No reagent, only heating. Okay, right? So that's about Fry's rearrangement. Okay, I hope you understand how it happens. Yeah.
Can you explain the first step again?
Yeah, first step, see, there is a bond here, right? There is a bond between this oxygen and this carbon, right? Now this bond is broken, this single bond is broken. So this bond will come here, means it is going to break and make a double bond. That is why you see there in the compound, there is no connection. This oxygen doesn't have a carbon, right? And after that, everything continues. That's it. Now this will come, this will attack, this will go here. That's it. This bond is already broken, right? So everything is satisfied. So for every compound, for not every compound, for every element in this, you would have broken one bond and made one bond. So now there is no charge, there is no excess positive charge, there is no excess negative charge. Everything is fine. Yes, understood?
Yes.
Okay, if you didn't understand, I can explain again. It's very simple. There is a single bond between these two. That is the first step, coming and making a double bond. And this bond will break, attacks here, this will go, that's it. This will end up in this, and tautomerization. That's it. Okay, right? Fine. So that's about Fry's rearrangement. Okay. Right. Anything else in this? Kolb's we said. Yeah. So these are all the different reactions possible with phenols and aryl ethers. Okay. Right. Moving on to aldehydes and ketones. Okay. Now aldehydes and ketones, we saw so many reactions, right? We know it can undergo oxidation, aldehydes can undergo oxidation to carboxylic acids, and aldehydes can undergo reduction to alcohols, primary alcohols, and ketones cannot be oxidized to any acid, right? But they can be reduced to secondary alcohols, right? And you know what are the reducing agents and oxidizing agents which you have to use. This and all were already discussed in the previous classes when we spoke about organic, right? Okay, now what will we do is we'll see the reactions which we didn't see at that time. Okay, so where we start with say a nucleophilic addition reactions. Right, so we saw electrophilic addition. Hope you remember. When I have C double bond Cs, right, you would have had at that time electrophilic addition reactions. Right, now we are going to see nucleophilic addition. And please remember, both in electrophilic addition as well as in nucleophilic addition, there are going to be electrophiles as well as nucleophiles present. Right. So how will you decide? How will you decide whether it's a nucleophilic addition or electrophilic addition? Is based on which attacks first. Right. So in electrophilic addition, it is always the electrophile which attacks first, and in nucleophilic addition, it is always going to be the nucleophile which attacks first. Okay, right? So pretty simple. When I have a carbonyl compound, right, and actually you see there is a nucleophile if it's coming, right? Now because of this bond being polar, there'll be a partial positive on this carbon, and there'll be a partial negative on this oxygen. Right. So this is the driving force for the reaction. Right. This carbon possessing a partial positive charge is the driving force for the reaction. Right. So now this nucleophile will come and attack here, and this bond will break. Right. So now I would have had CO minus with a nucleophile, and there's another bond. Right. So depending on whatever the solvent is, say if at all the solvent is water, Now this will abstract the H plus, right? So to form CO minus, OH and a nucleophile, right? So this is what is called as your nucleophilic addition reaction. Okay, right? Fine. So what and all can be the nucleophiles? What and all are the various reactions? Now we have already seen one reaction. Can you tell me what is that? We have already seen one nucleophilic addition already. Can you tell me what is that? Addition of what?
Halogens.
Halogens? No, we cannot add. We cannot. After all, the Cl minus. No, it is not going to work. But I'm telling you, we have already seen the reaction. Think of any nucleophile. Let me give you 10 more seconds, or else I'll answer.
Sir, alcohol.
Alcohols, yes, it is a good example, but we didn't see it yet. I know I'm going to form hemiacetals and acetals. We'll see that now. But we have not. That reaction is correct, but we didn't see that yet. We have already seen one reaction. We even did so many problems on that. Okay, so maybe I don't know. The answer is Grignard reaction. Is it not? What happened? R minus will come and attack here. So you'll form, say for example, if at all it was formaldehyde, it will always form a primary alcohol, right? And if it is any other aldehyde other than formaldehyde, you'll form secondary alcohol. And if it's a ketone, you'll form tertiary alcohol. This reaction you've already seen. R minus attacks, and then O minus will form the MgX, and then go for hydrolysis. O MgX is converted to OH. So many problems also we did on this. This is also an example for nucleophilic addition only, right? Okay, so fine, we'll move on. So hope it rang a bell in you, right? Okay, fine. So right, say first we'll take addition of HCN. Like this reaction is already there in your books, but still we are seeing it. Fine, no issues. So if I have a carbonyl compound, right, and if I put HCN, right, first the Cn minus comes, attacks here, this goes here. So now you will have CO minus Cn, and then obviously the H plus goes here, COH, Cn, and these are what are called as cyanohydrins. These are what are called as cyanohydrins. Carbon atom having one cyanide group and one OH group. Okay, right. So that is about HCN. Now you can even go for addition of alcohols, ROH, right? So in this case, you will see that there is a double bond O, a C double bond O. First comes RO minus, right? So this RO minus attacks here, and then this goes, right? Maybe I hope I can drop this part, right? So you'll see that I'm going to form CO minus, OR, right? And obviously I'll just put it, I'll directly put the H. One more step I don't want to write. Okay, so these are what are called as hemiacetals, right? What do you mean by hemiacetal? A carbon, if at all you see in a compound, a carbon atom having one OH and one OR at the same carbon atom, those are what are called as hemiacetals. Okay, so hemiacetals are formed when you have one alcohol molecule getting added to the carbonyl compound. RO minus first attacks, O minus then takes up the H plus to form hemiacetals. Okay, now if at all you had excess amount of alcohol, right? If at all you had excess amount of alcohol, what is going to happen? You will see that say one more RO minus will come, right? Now this RO minus can make this substrate undergo nucleophilic substitution, right? Nucleophilic substitution means obviously the OH minus will be replaced by the RO minus. OH minus is replaced by an RO, an RO minus. So you will have OR, OR, this other two bonds, whatever are they, right? So this particular compounds are what are called as acetals, right? So what is the difference between hemiacetals and acetals? Hemiacetals have one OH and one OR on the same carbon atom, and in case of your acetals, two ORs on the same carbon atom. Those are what are called as acetals. Okay, so this is an example for addition of alcohol. Again, nucleophilic addition reaction. Okay, right? Fine. Moving on. Third one is addition of ammonia and its derivatives. Right, addition of ammonia and its derivatives. Right, now it's pretty easy here. Say if I had C double bond O, again the mechanism is going to be very, very simple. Okay, now when I say ammonia derivatives, I'll write it like this: C double bond O is there. Ammonia derivatives means I have NH3. I remove one of the hydrogen atom from ammonia and put some other group. Okay, put some other group. So you are going to have, say, H2NZ. This Z is the other group. NH3 should have been there, right? Now NH2Z, if at all the Z is H, then becomes ammonia. Okay, now hope you remember how do you write the reaction. You just remove the water molecule and write it. Sorry, right? So you'll remove the water molecule, double bond O and a H, right? And you'll make the bond lengths. Right, so you'll form C double bond N Z. Okay, right. Now, when the Z, say I'm talking about Z and the product, whatever the product is called as, right? So if the Z, okay, fine, Z, the reactant name, the reactant, and the product. Okay, we'll make a table. Okay, so if this Z is OH, NH2 OH, it's called hydroxyl amine. Am I right? Yeah, hydroxyl amine, right? And what will be the product name? I forgot. Oxide. Thank you. Yes. Right. The product name NH2 C double bond N OH. If you have, that is called as oxide. Right. Now, if at all you have another NH2 as Z, NH2, right? It's called hydrazine. And this table will be given in your NCERT textbook also. And the product formed will be called as hydrazone, right? Okay. Then if you had, say, NH2CO, wait, there are so many things. Why am I not remembering? Say when you had R, NH2R, basically this is my primary amine. Okay, so primary amines will form imines. Okay, and what else? Secondary amine alone will have some difference, I guess. Right, secondary amine will form enamines, but we'll say that later. Okay, then you have semicarbazide and semicarbazone. What will happen there in semicarbazide? I'll have NH2 CO with a benzene ring, right? I think this is semicarbazide, right? Now the product will be semicarbazone. I can make it here. Okay, so like this, I'm going to have different ammonia derivatives getting added to form the product, addition product. Okay, now the mechanism will be little different, right? Little different in the sense that you will actually have one OH and one nitrogen molecule attached. Okay, that is going to become unstable. So some rearrangement will happen to give you the product. Okay, fine. But anyways, you don't have to worry about the mechanism. Just you can directly sketch the product now, right, with the help of a shortcut. Okay, right? Fine. So that's about addition of ammonia derivatives. Okay, what is the time? Fine. Next. Okay. Next one is going to be, I don't know whether you know this reaction. I have something called as in nucleophilic addition only, right? It's called Wittig reaction, not Fittig. Oh, we didn't see two reactions actually. Okay, we'll see that later. Maybe after this, we have to go back to alkyl halides and aryl halides, and we'll see that reaction. We'll see what is Wood's reaction, Wood's Wittig and Fittig. Like we'll see that. Anyways, okay. So Wittig reaction, what happens is you have a C double bond. Oh, this Wittig reaction is addition of ylides, right? So ylides are actually phosphorus containing compounds, right? Ylides are phosphorus containing compounds. Okay, fine. Again, it's going to be a complex mechanism, but we're not going to see the mechanism. What I'm going to have is this reacts with P PPH2. I don't want to say something wrong. Just give me a moment. Where are you? Okay, once again, guys, I'll be back. Okay, so it is like what I wrote is what I was about to write was correct only, but I was not confident. Okay, so it's basically PH3 plus CH2 minus. Okay, PPH2 plus with CH minus. Okay, or I can write it as some CH with R. Okay, now you don't have to worry about this. Whenever you see a phosphorus containing compound, this is the only reaction possible. Okay, there's no other reaction possible with the phosphorus containing compound. Okay, now how will you remember the reaction is you remove this C double bond O and you make the double bond with this. Whatever you see, the PPH3 plus will be common, right? Now there will be something else which is having the negative charge. You just remove this O and put this. So you will form C double bond CHR. Very simple. Okay, you remove the C double bond O and you keep CH. So you put the C double bond CH, and if at all this was CH2, you just put CH2 here. right? Or if at all there's any alkyl group, you'll put accordingly there. That's it. Very simple reaction. Okay. So there have been instances where questions were coming from this in JEE mains. Okay. So also, yeah, one of the important reactions. Okay. So addition of ylides. Ylides are phosphorus containing compounds. So PPH3, right, plus with a carbanion kind of thing, right? So you'll remove the C double bond O, and whatever is here, you'll just replace the double bond O with C double bond C. That's it. Okay, right? So that is about your nucleophilic addition reactions, right? Okay, then we'll go for the famous one, that is your aldol condensation, right? Fine. In aldol condensation, if we know what is going to happen, again, this reaction happens because of the acidic alpha hydrogen. That is the reason behind it, right? Okay. Say if I take a very, you must have been studying it, but we'll just start with an example, right? Say if I had CH3CHO, right? Now if I make a base or any OH minus or anything, or I'll just write a base, and I know this base is capable of removing the H plus from this alpha position. Correct, right? So now you will see that I'm going to form CH2 minus CHO, right? Okay, now you will see that there'll be another molecule. Okay, maybe I'll write it at the top. Okay, so there'll be another molecule of this CH3CHO. Now this will go on attack here, and this comes out. So we'll form CH3. Okay, fine. CH3, C double bond. I mean CO minus H, and this carbon is attached to this carbon. CH2, CHO. Right. This is my aldol, but this is my aldol reaction. Aldehyde and alcohol. Obviously, this has to accept a H plus to form CH3, CHOH, CH2, CHO. This is my aldol product. Okay. Now, aldol condensation product would be an elimination product. That's it. So you have to remove OH from this and H from this. Okay. OH from this and H from this. You will be ending up minus H2O. You will see that I'm going to have CH3, CH double bond CH, CHO. Okay. Now, what and all you can understand. Say what will they tell is they will give you 4 options. Okay. And ask you which among the following can be a product of an aldol reaction or an aldol condensation reaction. And again, I repeat, they'll give you 4 options, right? And ask you which of the following can be the product of this reaction, of this aldol condensation reaction. Now, what you have to understand is, people, aldol condensation can give either beta hydroxy aldehyde or ketone. Obviously, you see, this is my carbon atom, right? This is this is the carbon containing function. This is alpha position. This is beta position. So you'll always end up with beta hydroxy aldehyde or ketone, or you'll end up with alpha beta unsaturated aldehyde or ketone. Is it not? Now you see, this is the alpha position. This is the beta position. Alpha beta unsaturated aldehyde or ketone will always be a product. Okay. Right? So either you will get beta hydroxyaldehyde. These are the ways by which you will check in the question. You will always go for checking first. Beta hydroxyaldehydes are there. If it's there, yes, it can be a product of aldol reaction or aldol condensation reaction. If not, you will check for alpha beta unsaturated aldehyde or ketone. Again, you'll check in the 4 options, whichever is matching, then you'll take that option. Okay, right? Fine. So this is self-aldol reaction. Whatever you saw here, they have to use 2 molecules of this. So this is called a self-aldol reaction. Right. Now I can even have cross-aldol reaction. Cross-aldol, very simple. Cross-aldol means 1 molecule of this and another molecule of some other aldehyde or ketone. Right. So at that time, say if I use say what is it? Acetaldehyde. Right, this is acetaldehyde, and if I use for and if I react it with acetone, okay, tell me how many products are possible.
4.
Good, right? So you will have self-aldol of acetaldehyde only, self-aldol of the acetone only, right? Now this acting as nucleophile attacking the ketone, or ketone acting as the nucleophile attacking the aldehyde, you will get 4 products. Okay. Now every time you will not be able to go through the mechanism and get the answer, but again I would strongly suggest for you to go through the every time go through the mechanism if it's aldol and get the product. Now in this case, you have small molecules, right? But there can be cases where you will get a very big molecule. At that time, I will give you a shortcut eventually. I'm going to give you a shortcut. That's why I'm telling all this. If at all is a simple molecule, then you can use a shortcut, whatever I'm going to give you, right? But if not, then go by the mechanism. Okay. Now the shortcut goes like this. Okay. So if you had CH3CHO, let me write it like this: C double bond O and a H. Right. Now what you have to remove is alpha hydrogen. Right. Another molecule is alpha hydrogen is what you have to remove. Right. So how will I write this again is H2CH, that is CH3 with the CHO. Okay. Now what you is remove this. You will see that I have CH3, CH double bond CH, CH. This is exactly what I got. Okay. Now, if at all they're asking you what is the aldol product, just in the beta position, you add a water molecule to this, but make sure that in the beta position, I'm going to have an OH. That's it. Okay, fine. So we will take the acetaldehyde and acetone as an example. I'll give you 2 minutes. Use the shortcut and sketch all the 4 products. Obviously, one of them is already there. So 3 of them only you have to do. Quickly do it. Okay, this is acetaldehyde. It's self-aldol reaction. Go for self-aldol of acetone. Then you make sure that one of, like say, acetaldehyde acts as the nucleophile, and the next case make sure that the ketone acetone acts as nucleophile, and get me all the other 3 products. I'll give you 2 minutes. 2 minutes or so required. I'll give you 1 minute. Go for it. Okay, I hope you should have gotten it by this time. Okay, one product I already sketched, right? So now if I go for the self of acetone, so that would be CH3, I'll write it like this: C double bond O, CH3, CH3. Now you have 2 alpha hydrogens to be removed. So you write it like CH, H2, CH, C double bond O, CH3, right? Now what do? Remove this. So you'll form CH3, C, CH3, double bond, CH, C double bond O, CH3. That's it. This is the self-aldol product of this thing, acetone. Okay. Now I go for cross-aldol. Right. Say first case in the cross-aldol. Right. I put say CH3, C double bond O, H. right? And I make sure that the ketone is the one which is going to act as the nucleophile, right? So you'll write CH, C2, CH, C double bond O, CH3, remove this. So you will end up with CH3, CH double bond, CH, C double bond O, CH3. Okay, now the last one, I have to rub this part. If you take, can I rub this part? The first one. Okay. So the last one would be, okay, again like this, C double bond O, CH3, CH3. So in this case, I have to put CH2, CH, CHO, removing the water molecule. You'll get CH3, C, CH3, double bond, CH, CHO. That's it. These three will be the product. How many of you got all the three correct? Nobody got it. Or did even try?
I think.
Sorry?
I think I did, sir. I'm not sure if it's correct.
Okay, you think you got it. Fine, no issues.
Cross
I
ones I
think
didn't get, sir.
last one you got it.
Cross ones I didn't get, sir.
Cross ones you didn't get. Now you understood. Everybody understood.
Yes, sir. Now I did. Now I did.
Cross
Yes,
product? Very simple. Exactly same thing what you're going to do. Or if you find it difficult, if you find the shortcut to be difficult, go for the mechanism. Do not be lazy. It will take just 1 minute. Okay. In that 1 minute, it's not like you will be solving 5 questions. No, it's not like that. It's worth it to go by the mechanism. Okay. Do not worry about all that. Right? Fine. So yes, these are the products of the reaction between one aldehyde and another ketone. Right. Now, what will be there? What will not be there in your NCERT? This also will be there. Cross aldol will also be there. But what will not be there in your NCERT is, any guesses? Aldol only, but there's another type of aldol. Any guesses? What is the name going to be? Or how the compound will be? Any guesses? Whatever comes to your mind. Okay, I will not blame you because this is nothing. Okay, so third type of aldol is what is called as intermolecular aldol reaction or aldol condensation, right? So now tell me, what should be the condition for this reaction to happen? You can tell me, right? What should be the condition? From the name, what can you understand? What is the condition for this reaction to happen? Intramolecular aldol. Sorry, not intra. Till now, what you saw was intramolecular, between two molecules. Right? Intermolecular means, or, oh, I'm sorry, guys. This is intramolecular. I'm really sorry. Right? What you saw till now was intermolecular, between two compounds. Right? Now, what you're going to see here is intramolecular. That means I'm going to have only one compound. In that compound only the aldol reaction is going to happen. So what should be the condition?
In that molecule, there should be 2 ketone groups and aldehyde.
Definitely, there should be 2 carbonyl carbons. That's it. Okay, so only then that this kind of intramolecular reaction is possible. Okay, there should be 2 carbonyl carbons present. Okay, so we will take an example, something like this. Say I have CH3, CHO, CH2, 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 CHO. 1, 2, 3, 4. Or 1, 2, 3, 4, 5, 6. Okay, fine. Anything. Right. So you see there is a carbonyl carbon here, and there is a carbonyl carbon here. Okay. Now you will ask me, sir, if I put a base, there are so many alpha hydrogens, right? This is an alpha hydrogen. This is an alpha hydrogen. This is an alpha hydrogen. Right? So many alpha hydrogens are there. Which to remove? Don't worry about all that. Okay. What you have to understand is in this case, I am, so obviously you are going to say that I'm going to form a ring structure. Definitely I'm going to form a ring structure, a cyclic structure is going to get formed, right? Now, please understand, the first priority should be given to a 6-membered ring, right? It's the first priority should be given to a 6-membered ring. If you are not able to do it, then go for a 5-membered ring. This should be the first priority. Okay, the priority should be forming a 6-membered ring, and if it is not there, then go for a 5-membered ring. Okay, and if at all you're not able to form any of that, then go for whatever is possible. Okay, fine. Now, if for example, if I remove this alpha hydrogen, okay, if I remove this alpha hydrogen, and obviously what is the next step? This carbon ions should go and attack the carbonyl carbon, and it cannot attack this carbon, not possible, right? It will go attack this carbon, right? So how many membered ring will be formed? Can I say 1, 2, 3, 4? 4-membered ring will be formed, right? Now we'll check other possibilities, right? Say I will take, this is also an alpha hydrogen, right? Now this alpha hydrogen, say it attacks this carbon, what will be there? 1, 2, 3, 4. Again, a 4-membered ring is only possible, right? But if I take this alpha hydrogen and make it attack there, how many? 1, 2, 3, 4, 5, 6. A 6-membered ring is formed. Okay, now that can be one of the criteria. This is one way of looking at it. Second way of looking at it is generally ketones will act as nucleophile acceptors. Generally, no, I'm telling the opposite. Aldehydes are better nucleophile acceptors. Okay, can you come up with a reason for this? Now, in general, if I have any nucleophilic addition reaction, addition of HCN or addition of alcohol, whatever it is, generally aldehydes are more reactive than ketones. Can you come up with 2 reasons?
Due to less steric hindrance and electronic reasons.
Good, right? So one of them is steric hindrance. Ketones are highly sterically hindered because of 2 alkyl groups, right? And what was the other one you said?
The electronic.
Electron? I think you said it correct first time. Now only you are a little having doubt. Electronic reasons. Okay, electronic reasons, correct. Can you give me a solid explanation? Yes, electronic reason is the reason.
I kind of forgot that part.
Sir,
okay, no issue.
Aldehydes can have a better carbocation than
carbocation. No, Kana. Here there is no carbocation.
Or no, actually more partial positive charge or something.
Okay, that makes sense. Yes, that's the answer. Right. So please understand, people, if I have C double bond O, it's the nucleophilic addition, obviously steric reasons obviously matters. Right. Please understand, more and more is the positive charge on this carbonyl carbon, faster and faster will be the reaction. Is it not? Because nucleophile is negatively charged. So more and more will be the partial positive charge on the carbonyl carbon. Faster and faster will be the reaction. Right. Say if at all these were alkyl groups, I know what kind of groups are they. They are electron donating groups. Right. Alkyl groups are going to be electron donating groups. So obviously the amount of partial positive charge will decrease. Okay. So that is the reason why ketones are less reactive towards nucleophilic addition compared to aldehydes, because aldehydes have at least only 1 hydrogen, which is not going to do anything. Only 1 alkyl group will be there, right? So the amount of partial positive will be higher with in aldehydes than in ketones. So in both the reasons, either for steric reasons as well as electronic reasons, you will see that the aldehydes are going to be more reactive towards nucleophilic addition reactions. Okay. Now, in this particular case, what you understand is both these things are getting satisfied. Is it not? If I make the H plus removed from this, right, and I make it attack here, what I see is that definitely a 6-membered ring is formed. One priority done. Second priority is that generally I want aldehydes to accept the nucleophile, and that's exactly is also what is happening. This is an aldehyde, and that will be accepting the nucleophile. Okay, right. So this is how you look into it. But right, the questions actually will not like if they really ask you this, the question paper starter is in a really bad mood, is understanding. Okay, so this much and all they should not be testing you, but even if they test you, you are ready. Okay, don't worry. And one more thing I can say is there are certain bases. Okay, now you generally I'm gonna put a base, isn't it? Now if at all there is a strong base, there will not be any selectivity, right? It can abstract any of the proton if I have a strong base, right? So when I have a strong base, right, it has no selectivity. It can abstract any of the alpha hydrogen. Then it is not selective, obviously, because more reactivity increases, selectivity decreases, right? Okay, but if I use a base which is little weak, right, but I should not be using a base which is not capable of removing a proton. That should not be the case. Weak base, or I would say a weak sterically hindered base, right? So if I can use, I would say weak is also not, I'll not put weak also because that doesn't make any sense. Okay, so if I use a sterically hindered base, right? So sterically hindered base example can be something called as LDA. Okay, wait, lithium diisopropyl. Great. Okay, fine. Anyways, I'll tell you what is LDA in a few seconds. Okay, so this LDA is a very bulky base. Okay, right. So what it cannot do is that if, for example, for example, in this case, the particular case, in this case itself, right, I have 3 positions, 3 alpha positions are possible. I'm sorry. 3 alpha positions are possible, right? Now tell me, if I mark it as 1, 2, and 3, which is the least sterically hindered alpha hydrogen?
First one.
Absolutely, right? Because obviously in this case, you see there are 2 carbons, here also 2 carbons. Obviously, the first alpha hydrogen is going to be little less sterically hindered. So again, my LDA, the LDA will choose to get the proton which is least sterically hindered, because this is already sterically hindered. It will not be able to move into the bulk and abstract the proton. That is not possible. Okay, so if at all you use a base like LDA, remember that it is always going to get a proton which is least sterically hindered. Again, in this case, if I use LDA, whatever we want, this as well as LDA, all the things will give me the same product. Okay, I don't know, I just came up with a molecule randomly, but still everything is going good. Why not? We take it. Okay, fine. But again, this is too much for your level. You really don't have to worry about it, right? So if at all you want me to give you a structure for LDA, wait, I'll give you. I have to go for diisopropyl. Okay, so I have N. Diisopropyl amine. Okay, this is minus, this is Li. Okay, got it. Okay, diisopropyl amine. I know amines are a little basic in nature, right? So you see, these are 2 isopropyl groups, which makes it so bulky. Okay, anyways, you do not have to remember any of this. I mean, at least LDA if you can remember, well and good, right? Because they will not directly give you a base. They might still specifically tell it as LDA. That may also possible. Okay, fine. Anyways, so these are the things which you have to keep in mind for intramolecular aldol condensation reaction or aldol reaction. If you want to stop just with an aldol, well and good. Or if not, you can continue to form the alpha beta unsaturated aldehyde of beta. Okay, fine. We spoke about so many things. Fine, I'll give you 1 minute time. Can you sketch the product? Right, this, yeah, I told you what exactly is going to be there. I'll give you 1 minute time. Sketch the product. Remove this alpha hydrogen, make it attack here. That's it. That's all I want you to do. Go for it. Guys, do you guys watch WWE and stuff? I don't know. I know for sure girls doesn't watch, but there are few of my friends who are really interested. Girls, not girlfriends, friends and girls. Okay. So, anyways, so do you guys watch? Anybody is interested?
So I watched the UFC, sir.
UFC, yeah, that's better. Obviously, this
Yes,
is
sir,
like
much better.
WWE is masala, right? It's all scripted, I know, but that's why it is more interesting, right? So UFC, yes, is real fight, definitely.
Sir, did you watch McGregor versus Poirier?
Yeah. I saw. There was so much expectation from McGregor.
Yes, sir.
Right.
1 year break, sir.
Yeah, 1 year break. Still,
He's going
there are
down,
defeats which are needed. There are defeats which are definitely needed. Only then you'll be able to come back strongly.
Yes, sir.
Yeah. So today is Royal Rumble in for WWE. I don't know how many of you know it. Okay, so I hope you should have sketched the product by this time. Okay, right. So first step, if I put a base, I will form CH2 minus C double bond O, CH2, 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 C double bond O, H. Now this attacks here and this bond will break. Right? Okay, what will be the step? Okay, first I'll draw a 6-member ring. Okay, because I know 1, 2, 3, 4, 5, 6. 6-member ring is definitely there. Right? Okay, then you can put wherever you want, right? Okay, so what you understand is there is going to be one alcohol. This is going to form the alcohol, right? Okay, and that carbon obviously had a hydrogen atom. No issues, right? Okay, now what you see is the next. Okay, what you see is okay, with this carbon having alcohol, 1, 2, 3, 4. Fourth carbon from that, or if you come from the other side, now this is attached to this carbon, right? So this carbon, 1, 2. Second carbon from this side and the fourth carbon from the other side. However, you're going to get the same thing, right? Is having a C double bond, right? Say this, if I go from here, this carbon atom is having the alcohol. First carbon, second carbon is having a double bond. First carbon, second carbon is having a double bond. That's it. I got the answer. Right? So what you have to get? You have to get a beta hydroxy aldehyde or ketone. Right? You see, this is my position. This is my alpha position. This is my beta position. Yeah, you got beta hydroxy aldehyde or ketone. How many of you got this product?
I got it.
Good. Nice. Right? So easy, right? Like this, any kind of intramolecular or cross aldol or self aldol, all these reactions now you'll be able to answer. Okay. Now, what you see here is the condition. Yeah.
Sir, does the wedge and dash of OH and H matter?
No, doesn't matter.
Like if they give it to some options or something, will they give?
No, not exactly enough. That much and all they're not asking. No. Right?
So
but if at all, tell me, what is it?
That matters only when there's SN2, right, sir? Inversion of configuration or something.
Yeah. That's what it matters only when I have SN2. And also remember that if I go for E2 elimination, I will always go for anti-elimination product. So at that time, it is remember this thing. And also when there is something called a syn addition and anti-addition, right? So at those things, your stereochemistry matters. Yes. Okay. But this time, I really don't think so, right? Epimerization can happen. No, too much of an ask. Okay, they are really not going to test you all of that, right? Don't worry. Okay, fine. So that is about your aldol condensation reaction. Now, what you understand here is, right, if the only criteria for this reaction to happen is that I need to have at least one alpha hydrogen, correct? If I don't have alpha hydrogen, it cannot be removed and the aldol condensation reaction is not possible, right? But there is going to be some other reaction. Same thing, if I don't have an alpha hydrogen, right? But if I put a base, then also some reaction will happen. And obviously, I think you would have guessed by this time, the answer is going to be Cannizzaro reaction. Okay, so Cannizzaro reaction, we'll see what is the time. I think, yeah, we have 10 minutes. I'll complete. Okay, so Cannizzaro reaction is it's an auto oxidation reduction reaction, right? Auto oxidation reduction reaction. That means only one compound is there, or a better way, if I have to use a technical term, what will I use for this?
Redox.
No. One thing getting oxidized as well as reduced. What term will give?
Disproportionate.
That's it. It's also a disproportionation reaction. Yeah, it is redox, right? But still more technically, it's called a disproportionation reaction. Okay, fine. So what is going to happen? You already know what is going to happen here. If I have a, now the condition is no alpha hydrogen. Only then this is possible, right? So you see there is no alpha hydrogen here. Now if I put a base, or in specifically I have to, in this case it's not just a base, I have to put a OH minus. Okay, now I have to put a dilute NaOH, that's what they say, or concentrated NaOH. Anyway, it doesn't matter. OH minus is what is there, right? So you will see one thing will be oxidized product, COO minus, and the other thing will be a reduced product, CH2OH. That is very easy, right? Now, what is important is the mechanism again. I really don't think so in your school they would have taught you mechanism. You will see it now, right? Okay, fine. So what is going to happen is there'll be some strange things happening here, but do not worry, that's what is happening actually. Okay, so this is my benzaldehyde. Okay, so I'll take another molecule of benzaldehyde. Okay, now what is going to happen is the first step is from this, right? Okay, from this, I am going to remove H minus. From this, I am going to remove a H minus, minus H minus, right? So what will be remaining? Remaining would be C double bond O plus H minus, obviously. Okay, that is the first step, right? Now this H minus, okay, no issues. So this H minus will come here, attack this molecule, now nucleophilic addition, right? Now this molecule, and you'll see that I'm going to have CH2O minus, that will form alcohol, CH2OH. Done. One of the product you got. Correct. Right. Now I still have this. Right. Now this one, C double bond O plus, what I'm going to do is I have the OH minus now. Now this attacks the carbocation. That's it. So you see, this is one product, the second product. Now, you ask me, sir, what is the rate determining step? A rate determining step is the slowest step. This hydride transfer, this step is the rate determining step. Okay, hydride transfer is the rate determining step. And what you have to understand is the hydride comes from the aldehydes' hydrogen. The carbonyl carbons is hydrogen. That's what you need to remove. Okay, and that hydride goes as a nucleophile and attacks the other carbonyl carbon, and that is going to get reduced. This is exactly what LiAlH4 or NaBH4 does, right? LiAlH4 is going to give me the hydride, that will go and attack the carbonyl carbon, and that will get reduced, right? So in this case, the hydride is given by this aldehyde, and the carbonyl carbon is hydride. right? So that will go attack, and the next step is you have the carbocation formed here, then you have the OH minus present, that will go attack the carbonyl carbon to form COOH. That's it. This is how the disproportionation, oxidation as well as reduction happens for one single molecule. Obviously, you need to make two molecules. Okay, so that is about Cannizzaro reaction. Okay, what is the time? Okay, there are just two more reactions in reduction. Okay, so that is by for conversion of what is that? Conversion of carbonyl compounds to their corresponding hydrocarbons. There are two reactions. What are they? Conversion of carbonyl compounds to alkenes. What are they? It's there in an NCERT textbook. You must have written at least now by this time 2 times full-time exams, full portion exams. You must be knowing it. What is it? Something related to animal. That's the clue. That's the clue I can give you. An animal. Don't tell me humans are also animals. Yes, we are. But yeah, a wild animal.
Oh, Wolf Kishner.
Yeah. Yes. One is Wolf Kishner. Other one?
Clemenson.
Yeah. So Clemenson's reduction and Wolf Kishner's reduction. Right. So we'll just see those two. Again, not the reaction mechanism is not important. We'll just see the reaction and we'll wind it up. Okay. Right. So first we'll take Clemenson reduction. Right. So if I have a C double bond O and I have to go for wait. Wolf Kishner will be hydrazine. No. Anybody remembers what is the thing? Where are you? Yeah. Yeah, I got it. So yeah, zinc amalgam bar HCl. Zinc amalgam bar HCl, you are going to get CH2 with the other things, right? And when you go for Wolf Kishner, right? So you have C double bond O, then you will see that I am going for hydrazine molecule with water, right? Anything else? Oh, not only that, hydrazine molecule in the presence of NaOH, aqueous NaOH, right? So you'll see that again you'll form the same thing. Okay, so yeah, that's about your aldehydes and ketones. That's it, right? So there are so many reactions we already saw. That's why I didn't concentrate much. These are all the reactions which we didn't see. Okay, right? But still there are some not said on name reactions, but those are not important. Maybe after they complete the portions, everything completed, at that time I'll take it. There's something called as Kleinsen's reaction, Kleinsen's rearrangement. In this itself, I have Michael addition, Reformatsky, right? So all these things are there. But again, questions coming from that is very, very, for advanced, yes, those are very, very important. But for JEE mains, I've never seen questions coming from those. But still, once they complete all the portions, then if at all we have time, then we'll complete it. Okay, at least maybe you do the first attempt. After that, anyways, we have three months, right? One month, right? So at that time, we'll see whatever is remaining. Okay, so yeah, that's it, guys. That's it for today. Right? Any questions? If you don't have questions, we'll leave. Anything you want to ask? Okay, fine. Thank you so much. We'll meet tomorrow. We don't have class, right? So next class will be on Wednesday. Okay, fine. Thank you so much.
Thank you, sir.
Thank you, sir.
Thank you, sir.